Welcome back. If you have any questions, you're welcome to take your mute off and try asking them. I'd like to have interaction if you take an interest to do so. Today we want to talk about Green's theorem. We're getting close to finishing the book because we're skipping a couple sections on surface integrals. I want to mention those as we go along here. But we just don't, in this last semester of calculus, have quite enough time to cover everything in the book. It's the longest, hardest bit of material in there. But we'll at least begin the last chapter having skipped over the brief sections on surface integrals, which you can pick up pretty easily if you take the interest in it. And what this amounts to, Green's theorem, is a way to evaluate line integrals other than the two ways that we already have for a special case that comes up a lot in applications such as engineering. So far, we have two methods to evaluate vector line integrals. These are the line integrals that look like integral f dot dr, as opposed to the integral f of x y ds that looks like this. So we have the scalar line integral along a curve. Then we use it to define the vector line integral, integral f dot dr. For this one, which when f is a force, calculates the work done along the path c. We have these two theorems. One of them was that we could evaluate it, assuming enough derivatives existed, going over the values of t, a to b, of the curve, given parametrically, writing f along the curve. F is x of t, y of t, where x of t, y, and t are the parametric functions that tell you the coordinates as you move along the path. Dot, and you replace dr with dr dt dt. So there is how you can evaluate a line integral. Most generally. The trouble is, in lots of applications, this integral can be hard to evaluate. It just depends on what f is, really, and what the path is. Well, if f is conservative, there's a really nice result that makes this a whole lot easier, right? For a conservative f, think of a force, conservative force, with potential, thinking of potential energy, f of x, y, along a path c that goes from a point x0, y0, some point P with coordinates x0, y0, some point Q with coordinates x1, y1, and it doesn't matter what path you take to get there in a conservative case. You can take this path here as shown, or you go along some other path, or some other path. It doesn't matter which path you take. We say it's path independent. For a conservative force, your work is just the potential at the end point, x1, y1, minus the potential at the beginning point, x0, y0. So the book will sometimes write f of q minus f of p, or they'll write f of x1, y1 minus f of x0, y0. The conservative vector field theorem is that you can evaluate the line integral by taking the potential at the final point minus the potential at the initial point. So that was a nice theorem, but it only applied to conservative fields. So sometimes this integral is hard to evaluate because the path is nasty or the f is a bad function. Sometimes this one you can't use because it's not a potential, it's not a conservative field. What's another case that comes up a lot? It's going to be covered by Green's theorem. So we'll say alternatively, in a special case, so it's a special case like conservative fields are a special case, if your function f, and this one I'll write all the stipulations of the theorem. I left out the hypotheses of these two theorems here, some of them. If f of x, y is continuous, which we've been assuming in the other ones too. Am I going off the end here? Maybe a little. Okay. On an open plane region. So Green's theorem only applies in the plane. It won't apply in higher dimensions like these did. Containing a simple closed, sounds like a lot of stuff, but usually it's the case for any real life problems. Piecewise smooth curve C. Traverse counterclockwise. And bounding a simply connected region. What does all that mean? Open means you don't include the boundary. So it's like the interior of a rectangle, it's the interior of an ellipse, or interior of some curve. But you don't include the boundary. Simple means not self-intersecting. The curve doesn't self-intersect itself. Closed means it ends where it begins. So it doesn't intersect itself except that it ends where it begins. Right? So you can't do a figure eight like that. That's not simple. You can't do something like this. It's not closed, right? Doesn't end where it begins. Piecewise smooth means, well, smooth means it has a continuous derivative. Piecewise smooth means you can break it up into a finite number of pieces, each of which is smooth. So you're looking at a region like this. It's got a finite number of smooth pieces put end to end and traverse counterclockwise. Bounding a region simply connected means there's no holes in it. Can't even take out a point. There are interesting examples where you even take a point out of here and this theorem doesn't work. So region with no holes in it. Then this theorem applies to what we usually assume that F has continuous components. F1 of X, Y, I, F1 and F2, the things that multiply I and J. Then here's the theorem that applies. You can evaluate the line integral F dot dr by a double integral over the enclosed plane region R. I should put this. R here. Then you take the double integral over the enclosed plane region, df2 dx minus df1 dy dA. Now at this point, everybody's saying, oh, great, I turned my single integral into a double integral. Now I've doubled my work, right? You can, so you apply this thing sparingly. It's like integration by parts, right? Sometimes it makes it harder. Sometimes it makes it easier. You just have to make a judicious choice. And the idea here is when R is a really easy region, like a rectangle or a circle, then this can be a really great theorem because integrating over the region, if it's a rectangle, has constant endpoints, and if it's a circle, in polar coordinates has constant endpoints. That makes it very easy to do this integral. Maybe easier than going around the boundary here, where you have to break the rectangle into 4 pieces to evaluate it along each piece of each edge of the rectangle. Or you have to write the circle and have a complicated integrand because of the polar coordinate transformation. So this thing actually can make your integration easier. Call that equation 1. And furthermore, this thing goes both ways, right? I can take some integrals over plane regions and rewrite them as line integrals, single integrals. So actually, sometimes use this the other way and write a double integral as a single integral. One of the interesting problems in the section is that you can evaluate by making this equal to 1, so that the right side is the area of a plane region. You can evaluate the area of a plane region as a line integral. In other words, with certain line integrals, you can integrate along the boundary of a plane region in a certain line integral to get its area enclosed. And that kind of an interesting result. You integrate along the boundary to find the enclosed area. But that's actually a consequence of Green's theorem. Oops. Oh, pushed the wrong button. Make you dizzy for a little while here. All right. So let me pick an example here. By the way, I want to make an interesting note on this, in addition to the theorem. When we are writing this theorem, the book keeps changing notations. When you see this, integral f dot dr along a curve C, or you see this, integral f dot t ds, or you see this, integral f1 dx plus f2 dy, where f1 and f2 are functions of x and y. Which one does Green's theorem apply to? It actually applies to all three. These are all just different notations for the same thing. This is how we define the vector line integral, where t, recall, is the unit tangent vector along C. As you move along C, suppose I'm going counterclockwise like the theorem says. This f dot t, integrated as a scalar line integral, is actually how this vector line integral was defined. What does this mean? This notation is supposed to mean this. It's just short notation for this. And this notation also is a short notation for this. This one is suggested because if you divide by dt here and multiply by dt outside so that the integral runs over t going from a to b, this is our first theorem for how to evaluate it. So this one is suggested for how to evaluate it. You divide by dt inside, multiply by dt outside. You can integrate over the t values a to b and evaluate this thing. But all three of those notations will mean the same thing. When you see those, just think Green's theorem or whatever other method. We've got two other methods before that, but keep that in mind. When you see the final exam, I want you to be able to do all three cases. Be able to do the general case where you just evaluate the line integral by that first theorem, applies quite generally. The second one applies only to conservative forces, and this one, Green's theorem, applies only to simple closed piecewise smooth curves, enclosing a simply connected region, a region with no holes in it. Now I said traverse counterclockwise, but let's make a second note. Suppose I traverse it clockwise. If I have a counterclockwise curve C, then I can write from minus C notation to indicate the same curve traveled the other direction, in this case clockwise, if C was counterclockwise. And we have this theorem. You can prove it from evaluation formula 1, but it actually applies in some other cases. The line integral traveling C backwards, we call that minus C, is minus the line integral traveling C forward. So unlike the scalar line integral, it gives you always the area under the curve, the area of the curtain below the surface, if the surface is over the plane region you're looking at. And it doesn't matter which way you go from one end to the other. That's the scalar line integral. The vector line integral is dependent on which direction you traverse the path. If you go the path one way, you get minus the value you get traveling the other way. So with those reminders of notation and of traveling curves backwards. Let's try.
Professor Stapleton,
Yeah.
can you like explain what next to the note, like on the far right, the third thing that's equal? We can't really read that.
Oh, sorry about that. Yeah, it's integral f1, a function of x, y, dx, plus f2, a function of x, y. Maybe that's big enough, dy. Is that big enough now? I hope. So that's the third notation. See, a function dx plus a function dy, that's just another notation that means this. This one is real confusing. When you see it, you say, where did I see that before? But it's just notation for this. All right. Let me move this over to the other side then. Oops. Let's try this. Suppose I want to evaluate the line integral, in this case, along a closed path of the kind we just indicated, of y minus x cubed dx plus x plus y squared dy. I think I wrote that down right. No, I wrote it backwards. I wanted y minus x cubed. Let's see. X minus y cubed on the first one. Oh, I wrote it wrong. It won't hurt much, but let's try this one. X minus y cubed. And y plus x squared. All right. I don't think it changed the problem too much, but let's stick to the one I have written up. Suppose we evaluate this line integral by Green's theorem, where we want to evaluate this over the following region. It's the unit circle, x squared plus y squared equals 1, traveled counterclockwise. Again, if you want to do it clockwise, you just do the same computation, put a minus in front of it. I like when we're first doing this to draw the picture. I think that makes it a whole lot more understandable. The idea is a line integral f dot dr is how you calculate work, if f is a force. So think of traveling through a force field. How much work do you do? Traveling along this path counterclockwise, which is the unit circle. So that's the curve C. And then the plane region that the theorem refers to is the enclosed disk. These components of the function are polynomials in two variables, so they're continuous everywhere. All the theorem, and there's no holes in this region, all the hypotheses of the theorem hold. We can apply Green's theorem. Alas, it doesn't look like f dot dr. What is it? Well, remember, this is the alternate notation. Whatever multiplies dx is f1. Whatever multiplies dy is f2. And this is just another notation for f dot dr along C, where f has these components, x minus y cubed I, and x plus y plus x squared j. So that's what we're doing. This is just another notation for doing this line integral with that vector field. Green's theorem then says this, if we apply equation 1, we say, well, it's the double integral of df2 dx minus df1 dy. dA evaluates that. Right? Over the plane region that's enclosed, which means this unit disk. Well, what's F1 and F2? F1 is what multiplies dx, F2 is what multiplies dy. So df2 dx is 2x. df1 dy is minus 3y squared. I wrote this thing down backwards again. Oh, okay. Let's see. Actually, I had it this way. Call this x cubed. Just to keep to my problem. I couldn't read my writing. That's x cubed. Then df2 dx is 3x squared. And df1 dy is minus 3y squared. So I have minus 3y squared. And I have this. There we go. Sorry. df2 dx, partial of that with respect to x, minus partial of this with respect to y. Well, this is the double integral over the disk then of 3 times x squared plus y squared. dA. And Green's theorem has actually made this a lot easier because the integrand happens to be simple in polar coordinates and the region of integration happens to be simple. Since I'm integrating over the disk, I just let r go from 0 to 1 and theta go from 0 to 2 pi. Integrates over this plane region. Simple polar region, we sometimes call it. And the integrand now becomes 3r squared, and then dA becomes r dr d theta. And now I've got a fairly simple problem, right? I'm integrating 3r cubed, gives me 3r to the 4th over 4. I'm going to plug in 0 and 1, and then I've got to integrate that with respect to theta. Well, this is just integrating 3/4. You get 3/4 theta from 0 to 2 pi. Gives you 6 pi over 4 or 3 pi over 2. So there's the evaluation of a line integral using Green's theorem. Let's try another one here.
Professor Stapleton, could you explain what is 3 pi over 2? Like, what does that mean with relation to like the picture that you drew?
Oh, it's saying that the work taken along the path, my computer's running out, I'm gonna move it here. It says if you take the work taken along this path, it's equal to 3 pi over 2 joules or whatever unit of energy you have. The idea of work is you've got this force field, and I don't know how to sketch it, but it's got a vector associated with each point. This is F. At each point x, y, it gives you this times I plus this times j. And then as you're moving through this force field along the path, maybe this is a gravitational field pushing you through. At any point you're at, there's a unit tangent vector t. And the line integral can be written as integral f dot t ds. In other words, you go around the curve taking the component of the vector field. If this is f, you take its projection in the direction you're moving. And you say, this is the component of force in the direction I'm moving. And I integrate that force along the length of the path, and I'm essentially taking force times distance, but the force is changing. And so it calculates the work going around this path within this force field is the idea.
Thank you.
So yeah, so it's evaluating the line integral by changing it over to a double integral instead over the region that it encloses. But that's what the line integral means. The most easy application is work. Well, let's try this one. This one I can memorize better. Suppose I took the integral of minus y dx plus x dy along the curve C, be my second example, where C is traveling around the unit square. This is really set up ideally for Green's theorem. You'll see why in a second. Here's my path, and suppose C is traveled counterclockwise, again, around this unit square. Here's the enclosed region R. Now I found the work if I were to go all the way around this path once. How can I evaluate it? Well, what's nice about this for Green's theorem is even though it converts it into a double integral, what you do is you write immediately, f1 is whatever multiplies dx, f2 is whatever multiplies dy, and by Green's theorem, 1, this is df2 dx minus df1 dy, dA over the region enclosed. Well, let's see, df2 dx is 1. df1 dy is minus 1. So I just have integral of 2 dA. I'll pull the 2 out and say it's 2 twice the double integral over the region dA. How easy is that? I don't even have to write down the limits of integration. Why not? Because this double integral dA is just the area of the enclosed region, enclosed square. It's a 1 by 1 square. So the area is equal to 1 squared, or 1. This line integral, I just do 2 units of work moving around this path. So this one just evaluates the 2. Look how easy this made it. If I were to apply this directly with the first theorem I wrote today, I'd have to take the line integral along this part plus the line integral along here, here, and here. I'd have to write 4 parametric curves and evaluate with that first theorem all 4 line integrals and add them together. But if I put it to Green's theorem, I can do it all in one fell swoop. I just take 2 times the area of the square. So once in a while, Green's theorem will save you a lot of work for very simple regions like rectangles and circles. Well, it gets more complicated as always, right? That's the way these sections are, they always build. We now want to discuss Green's theorem. By the way, we'll finish this next time. I won't be able to quite finish everything today. Green's theorem for multiply connected regions. We said the theorem doesn't apply if you had a hole in the region. So what's going to happen in engineering, of course, somebody's going to do something with a hole in it, right? Suppose, for instance, I have a region like this that's bounded by a curve C1. And now inside it, I have another curve, C2, traversed in the opposite direction. And each of these things satisfies the hypotheses of Green's theorem individually. And then there's a function f, which gives you a vector field. let C be the union of these two curves, the outside curve and the inside curve. And suppose my region does have a hole in it, so Green's theorem doesn't apply. Well, here's what you can do. It's maybe what you guess. The line integral along C, the union of these two curves, f dot dr. The work I do traveling around this path and then carrying it over here and walking around this path, the work that the force does, is equal to what? Well, if you think of this way, suppose I break it up into two pieces, like this maybe. Because these are opposite direction, I can traverse this pink path this way, call that CA. And maybe I need one more color of blue path, how about? There's a blue path. CB, suppose we travel that one counterclockwise too. Green's theorem applies to each of these two regions. We can say that this one, this line integral around the union of these two curves, because going this way with the red and this way with the blue cancels, and going this way with the blue and the opposite way with the red cancels, remember they're minus each other. The line integral around the union of these two is actually equal to the line integral around CA f dot dr plus the integral around CB f dot dr, both taken counterclockwise. So I have that, right? But now this one Green's theorem applies to because it now has no holes, and this one Green's theorem applies to because it now has no holes. This is equal to the double integral df2 dx minus df1 dy dA taken over region R1, since Green's theorem applies to it, plus the double integral over region R2. Same thing, Green's theorem applies to region R2, df2 dx minus df1 dy dA. And when you add these together, what are they? Well, that's just the union of the integral over the two regions. So it amounts to this result that I've derived. I thought I had this to the end. Can you see that all right? I hope. I'll run it back to the other end. So we'll say, hence, what we've derived is this. This is it. That was the proof. We can call this equation 2. For a multiply connected region where the outside curve goes counterclockwise, the inside curve goes clockwise, the double integral over C, the union of those two, I'm sorry, the line integral over C, the union of those two, is equal to the sum of those double integrals, which is the double integral over R, the union of R1 and R2. I'm sorry, not union, R1 minus R2. No, I'm sorry, R1 plus R2, there we go. The two regions there, RA and RB, what I should call those. What I call them? No, I call them R1 and R2. Anyway, should call them RA and RB. All right. df2 dx minus df1 dy dA. The sum of those two integrals on the right is equal to this integral over the region that's their union. Let's put it that way. Where maybe you can't see it so well, but we'll call this RA the pink region and RB the blue region inside the blue curve. All right. Well, scratching this out, this is just the region without the hole, or the region having a hole in it between C1, the curves C1 and C2 enclosed. So that's Green's theorem for multiply connected region. I could call that 2. This Green's theorem really applies also to these. You write the same theorem for a region with a hole if the outside curve is traversed counterclockwise and the inside one is traversed clockwise. And you can do this with more holes in it too. You just have to put them all together here. So Green's theorem for multiply connected R is that. Now we need another example for this one. Suppose we do this. We want to evaluate let's see, integral of x squared plus yi plus, of all things, 4x minus cosine yj this dot dr. I suppose we want to do this over the following region that has a hole in it. You go from 0, 0, up to 5, 0, up to 5, 5, back to 0, 5, back to the origin. Counterclockwise, call that C1. And then I'm going to take a hole out of it. I'm going to go in the middle from 1, 1 to 3, 1 up to 3, 2 over to 1, 2 and back to 1, 1. Except this time I'm going to go the other way. I'm going to go clockwise and call that C2. How can I evaluate the line integral around C, the union of those two curves, C1 and C2? Well, this is exactly what Green's theorem for multiply connected regions is for. You have counterclockwise on the outside, clockwise on the inside. The region between them looks like that. Has a hole in it, but Green's theorem applies by the derivation we just did. And we call whatever multiplies I F1, whatever multiplies J F2, and we apply Green's theorem for multiply connected regions too. We'll say this is the double integral over R, this enclosed region with a hole in it, between the two curves, of df2, which is 4x minus cosine y dx, minus df1 dy, which is partial of x squared plus y. Need to move this. Dy dA, so there's Green's theorem. You rewrite it as a double integral over the enclosed region. Well, you converted your single integral into a double integral, but it's actually easier because now it's over a square with a rectangular hole, R. So we could say this is, well, d4x dx is 4, derivative of cosine y is 0, you just get 4. This one is derivative of 0 plus 1. So I have this integral to evaluate. Well, this is just integral of 3. The 3 comes out. The integral of the plane region is the area. So it's just 3 times the area of the region with the hole missing is 3 times, well, the outer square is 5 by 5, so its area is 5 squared. The hole we took out is 2 by 1 for the rectangle. So it's 25 minus 2 is 23. 3 times 23 gives me 69. Is the line integral around the union of those two curves. There's a problem that's really screaming for Green's theorem, right? If you did it by the ordinary way, the first equation we wrote, you take 1, 2, 3, 4, 5, 6, 7, 8 different parametric curves. These you'd have to take minus the line integral because they're clockwise. Right, this thing with a cosine y would be terrible, but everything would cancel out and you wind up with 69 when you're all done. Green's theorem was a lot easier for that. Well, one last application. We said that in some applications, it's nice to go from the double integral back to the single integral. Let's try Green's theorem to evaluate an area. And here's the derivation of that one. I like to put it down because once you see it, you can remember this and figure it out if you had trouble otherwise. Suppose that I have a vector field f of x, y that's x, j. All right. Then Green's theorem, equation 1, becomes what? It becomes line integral of 0 dx plus x dy. That's the line integral corresponding to this f2 and f1 equals 0. So it's 0 dx plus x dy equals the double integral of, well, the f2 dx is dx dx minus the f1 dy is 0. dA over the region enclosed becomes double integral of 1 dA, which is actually equal to the area. What I just showed is that you can evaluate the area of an enclosed region by integrating the line integral x dy along the boundary. How about that? So the area can be evaluated by the line integral going along the edge. Alternatively, suppose f of x, y is minus y, I. Then what do we get? Well, the line integral of minus y dx along C, and maybe I should put this little circle. The circle is optional to put on, but it indicates you have a closed curve is what all it indicates. Sometimes people put an arrow to indicate which way it goes, counterclockwise or clockwise too. That's optional too. But this just reinforces that we have to do a closed curve for Green's theorem. Minus y dx is this one is also equal to, by Green's theorem, 1 df2 dx, let's see, df2 dx, which is 0, minus df1, which is minus y. Let's put minus y on the inside, doesn't matter. D minus 1 minus y dy dA. Well, the integrand here once again is 1. Integral of 1 is the area. The area can be evaluated by taking minus line integral of y dx around the curve. Or you can average these and say the area is actually equal to 1/2 the sum of these two integrals. You can say it's 1/2 the line integral around the closed curve of x of minus y dx plus x dy. So we actually have three formulas here. You can take out the intermediate step, that's the derivation. For evaluating an area by integrating a curve along its boundary. Well, it looks like I'm out of time, so I'll do an example of that beginning next time. It's kind of an interesting result, I think. Green has a nice write-up on Wikipedia. Maybe you want to look at it. Maybe I'll put it up on the video. Thank you for your time this morning, and I'll see you next time.